Hey guys, continuing on chapter 9, we have estimating the population mean. So the previous one was estimating population proportion. This one's going to be population mean. Again, a point estimate is a value of statistic that estimates the value of a parameter. So a point estimate in this case, we have our sample mean. So we have X bar. And we're going to use that to make an estimated guess of our population mean or mu. So for example, X bar is a point estimate for the population mean. Now looking at this, the website fueleconomy.gov allows drivers to report their miles per gallon of their vehicles. The data in table 2 show the reported miles per gallon of a 2014 Toyota Camry automobiles for 16 owners. Obtain a point estimate of the population mean miles per gallon of a 2014 Toyota Camry. All right, so starting off with this, we have to take this over to Excel. So let's copy this data. And come over here. So insert data from table. And it looks like it would be this one here. All right, so it looks like it didn't catch everything correctly. It used like a little dot instead of a period. So I'll fix this off camera. All right, so now that we have all of this here, we could find our point estimate. So remember, a point estimate is just a sample parameter or sample statistic. There we go. So here we have X bar. So we're going to look at the sample mean. So equal to average of the data set. There we go. And while we're at it, we could also get the sample standard deviation S. So here that's going to be equal to STDEV for standard deviation. If is it standard deviation P, standard deviation of the population, or standard deviation S, standard deviation of the sample. It's going to be this one because the data is collected from a sample and not a population. Perfect. So now that we have X bar and S, we can go back over here. So sample mean, again, all we did was we added all the data up and divided by the number, and we got 28.1, 28.1, perfect. So the point estimate for mu is going to be 28.1 miles per gallon. Remember, round the statistic to one more decimal point than the raw data if necessary. Next, state properties of the student's t-distribution. So normally we have the Z, the normal distribution, but here we're introducing the student's t-distribution. So it comes with its own properties and other things. So suppose a random sample of size n is taken from a population that follows a normal distribution. The distribution of t is going to be this right here. So remember with the z-score, we have our value minus the mean divided by our standard deviation. So in this case, our standard deviation is not just S, it's S divided by the square root of n. Then we still have mu, we still have X bar and all that other stuff. So that follows the student's t-distribution with n minus 1 degrees of freedom. So degrees of freedom is always going to be 1 minus the number of the sample size. So just keep that in mind. And where X bar is the sample mean, S is the sample standard deviation. Use statistical software such as Minilab or Minitab or StatCrunch to obtain 2,000 simple random samples of size n equaling 5 from a normal population with mu equaling 50, standard deviation equaling 10. Calculate the sample mean and the sample standard deviation for each sample. So again, the z-score, we're changing it from z-score and we're looking at the t-score. So z-score of all this data, t-score of all this data, and draw the histograms for both. So with Minitab, what they did is they looked at these values. They said that the mean was 50, standard deviation 10, sample size 5. And they did the same thing over here. So we're looking at the exact same data on the normal distribution and on the student's t-distribution. So normal distribution here, student's t-distribution here. So normal distribution, we got the data, looks roughly symmetrical. And by roughly symmetrical, we kind of mean just roughly bell-shaped. So roughly bell-shaped here. But if you look at this too, it looks roughly bell-shaped as well. So both of them look roughly bell-shaped, so we could keep that in mind. The data on the left-hand side looks to be smaller than it is on the right-hand side. And let's see if we have any other similarities. So notice a histogram of figure A is symmetric and bell-shaped with the histogram centered at 0. Vertically, all the rectangles lying between -3 and 3. In other words, Z within n equaling 5 follows a standard normal distribution. Cool. The histogram for T with n equaling 5 is symmetric, bell-shaped, centered at 0, but the histogram of T has longer tails. So let's take a look at that. So the longer tails, we have -10 over here, +7.5 over here. So we kind of went further on either side. Let's see. The histogram with T5, symmetric bell-shaped, centered at 0, histogram has longer tails. That is, T is more dispersed. So it is unlikely that T follows the standard normal distribution. So the additional spread is due to the fact that we divided by the standard, or divided by the standard deviation of S divided by the square root of n to find T, instead of the standard deviation sigma divided by n. So repeat for part A for 2000 simple random samples of size n equaling 10. So looking at this one, our data is a little tighter for our t-distribution. Our normal distribution still kind of follows the normal distribution here. Did a little something crazy here, but still roughly our normal distribution that we're used to. Over here, the sides came in a little bit. We could see that the data got a little bit smaller on the ends. So we see that because earlier we had -10 over here and a +7.5 over here. So data kind of scrunched up a little bit more. For B, histogram of figure A is symmetric, bell-shaped, centered at 0, vertically with the rectangles lying between -3 and 3. In other words, Z with n equaling 10 follows the standard normal distribution. The histogram of T with n equaling 10 is also symmetric, bell-shaped, and centered at 0, but the histogram has longer tails than the histogram of Z with n equaling 10. So T with n equaling 10 also does not appear to follow the standard normal distribution. I'm going to save us some time and just show the different properties of the t-distribution, and we could compare it to the normal distribution. All right, so the t-distribution is different for different degrees of freedom. So let's see if we get a picture of this. So it's different for different degrees of freedom. Some of them are taller, but the area underneath the curve is always still going to be 1. So noticing those difference. So T is a normal distribution, or the blue one is a normal distribution. The red one is n equaling 15. The orange one is n equaling 5. So the area with the green area is n equaling 5. So it's a little bit fatter this side. It's a little shorter this way. These are a little bit taller, but the area for all of these is still going to equal 1. 2, the t-distribution is centered at 0 and is symmetric about 0. So same thing as the normal distribution. Area under the curve is equal to 1. The area under the curve to the right of 0 is equal to the area under the curve to the left of 0, which is equal to 1/2, just like the normal distribution. As t increases or decreases without bounds, the graph approaches but never equals 0, just like the normal distribution. The area in the tails of the t-distribution is a little greater than the area in the tails of the standard normal distribution because they are using S as an estimate of sigma, thereby introducing further variability into the t-statistics. So remember, the larger the sample size, the more normal we are. The larger the sample size, the more normal we are, even with the t-distribution. So it approaches a normal distribution. But again, we have something that looks like this. Area is still equal to 1. Things are still roughly exactly the same. 6, as the sample size n increases, the density curve to t gets closer to the standard normal density curve. This result occurs because the sample size n increases the value of the s getting closer to the value of sigma by the law of large numbers. Again, we have a t-distribution with different degrees of freedom compared to the normal distribution. And now finding t-values. So now we're looking at the relevant information for this section. So the notation z sub alpha is used to represent the z-score whose area under the normal curve to the right of z sub alpha is alpha. Similarly, let t sub alpha represent the t-value whose area under the t-distribution to the right of t sub alpha is alpha. So very similar to the normal distribution, but this one is the t-distribution. We have different values for these. Find the t-values such that the area under the t-distribution to the right of the t-value is 0.10, assuming 15 degrees of freedom. That is, find t sub 0.10 with 15 degrees of freedom. All right, so let's draw our situation. So here we're still drawing like what we would see as a normal curve, because eventually this does replicate a normal curve. All right, so find t-values such that the area under the t-distribution to the right of the t-value is 0.1. So to the right of the t-value 0.1, we're going to say that's our t-value. So t sub 0.10. And we have 15 degrees of freedom. So they did not give us n, they actually gave us our degrees of freedom. So degrees of freedom is equal to 15. And that's actually all that we need for our curve over here. So here we're looking for the associated t-value. So t of 0.10, that's equal to, this is the student's t-distribution. So t-distribution or t-inverse. Do we need an area or do we have an area? In this case, we have the area that we're looking for the associated t-score for. So we're going to use t-inverse. And here the probability to the right is going to be 0.10. But actually the data that we're looking at is all the area to the left. So we're going to look at this right area right here. So here the probability is going to be 0.9 instead of 0.1, and degrees of freedom is 15. And there we go. So the t-value, t of 0.10 is equal to 1.34. 1.34, depending on how far they went out. Okay, so they did this area to the right of the tail. So when you look at a table, they actually give you either right tail test, left tail test, but we're always going to use Excel. And they went out 3 decimal places, so it's 1.341. 1.341 is what they got here. Perfect. So the critical value of z with an area to the right of 0.10 is approximately 1.28. And let's see if they're telling the truth. So equal to the z of 0.10 That's equal to the normal distribution, normal inverse, because we have an area, probability was 0.9, mean 0, standard deviation 1, because we're looking at the standard normal distribution. And this is what we would have gotten if we had a z-score. So using the normal distribution, using the t-distribution. So that's the difference between the two. 0.12 or 1.28, sorry, 1.28, which is smaller than the critical value of t with 15 degrees of freedom. This is because t distribution has more spread than the z distribution. All right, just so we could kind of see the difference in stuff. If we get a rather large distribution, we start getting closer and closer to the normal distribution. So here, our sample size of 100, I think they say that 30 makes it roughly normal. But anything larger, we could say 500. It starts getting closer and closer to the normal distribution. But let's go back to what they wanted here. All right. Next, construct and interpret a confidence interval for the population mean. All right, constructing a 1 minus alpha times 100% confidence interval for mu, population mean. So first, provided sample data come from a simple random sample or randomized experiment, the sample size is small relative to the population, or we could say that the sample size is less than 5% of the population. The data come from a population that is normally distributed, or the sample size is large. So with that, we have our margin of error. So for all of these, we're always going to have a margin of error. We always have our point estimate, so our sample data. We have our margin of error that we're going to either add or subtract, and that's going to give us our confidence interval. So here the margin of error is our critical value times our standard deviation. So the standard deviation is sample standard deviation divided by our square root of n. Because this confidence interval uses a t-distribution, it is often referred to as a t-interval. Margin of error, again, is our critical value times our standard deviation. So critical value times s divided by the square root of n. The normality condition. So when Gossett developed the t-distribution, he assumed the sample data came from population that is normally distributed. Most distributions are not exactly normal, so we need to verify that the sample data appear normal enough before using the t-distribution to construct confidence intervals for the population mean. So we have two options. Option one, the better option. So if n is less than 30, draw a normal probability plot to check the normality condition of the box plot to check for the outliers. The data appear to come from a population that is approximately normal with no outliers, and it is reasonable to use the student's t-distribution to construct a confidence interval for the population mean. Option two, so this option relies on the robustness of constructing confidence intervals using the student's t-distribution. So an inferential method is robust if it is accurate despite the minor departures from its underlying assumptions, such as the assumption of normality in the student's t-distribution. For n less than 15, student's t-distribution, use students' t-distribution to construct confidence intervals about the population mean if the sample data are symmetric with no outliers. The data should not be skewed left or right. This condition may be verified with a box plot. The median should be in the middle of the box and the whiskers should be of equal length. For data between 15 and 30, use the student's t-distribution to construct intervals about the population mean, provided that the sample data do not have extreme skewness and no outliers. If n is greater than 30, use the student's t-distribution to construct confidence intervals about the population mean. Even for skewed distributions, this relies on the central limit theorem for distribution of the sample mean to be approximately normal. Law of large numbers for the sample standard deviation to be close to these population standard deviation. Okay, so after all of that, we could just use the student's T distribution. So the web fueleconomy.gov allows drivers to report the miles per gallon of their vehicle. The data in table 3 show the reported miles per gallon of 2014 Toyota Camry automobiles for 16 different owners. Treat the sample as a simple sample of all 2014 Toyota Camry automobiles. Construct a 95% confidence interval for the mean miles per gallon of a 2014 Toyota Camry. Interpret the interval. All right, so we have this data. Let's copy it. And now that we have that, we could come over here. So insert data from table. Much better. Found it. And it looks like there's a couple mistakes here. So I'll do this off camera and I'll come back. Okay, so now that we have our data here, let's grab all the necessary information. So we definitely need P, or not P hat, we need our sample mean, X bar. So X bar is equal to the average of this data set. Perfect. Then we need S, our sample standard deviation. So this is equal to STDEV of the sample. Get our data. Perfect. N, we could say is equal to the number value of these data set. Oh. Or we could just look at this. So 1, 2, 3, 4 by 1, 2, 3, that's 12. Since we're working with the T distribution, we could also get our degrees of freedom. So degrees of freedom is equal to our sample size minus 1. So perfect. And I believe that's all that we need to construct an interval, right? So 95% confidence is what we're looking for as well. So confidence is 95%. And let's stretch this out just so we could see the full word confidence. All right, so now that we have all of this, we could construct our confidence interval. So remember the T distribution. So in order to find out what E is, so our margin of error in this case is equal to T sub C, our critical T value, times our standard deviation, which is S divided by the square root of N. So we have S, we have N. So the only value that we're looking for right now is going to be T sub C. And to get our critical value, let's go ahead and draw a picture illustrating what we're going to do. So with 95% confidence, we want 95% of the data to fall here. So that would be 0.95, which means this left side and this right side could take on that extra 5%. So this is going to be 0.025 and 0.025 here as well. So over here, our T value is going to be made up of this area here. So that's going to be T sub 0.975. So here we're looking for T sub 0.975. So our T value is going to be equal to T distribution. So T distribution or T inverse, do we need an area or do we have an area? In this case, we have an area that we need the associated Z-score or T-score for. Here, the probability is going to be 0.975. And degrees of freedom, perfect. We already have our degrees of freedom right here. And now we have our t distribution. So now in order to find E, we just have to find these values right here. So S, and what we could do is shift these down so that way we could have S divided by the square root of n. Do we have a square root sign? I think we might have a square root sign. Let's look for it. I'll do this off camera. Okay, so I did find the square root symbol and we have square root of n. And there we go. All right, so equal to S divided by the square root of n, which is SQRT of n. There we go. So we have S divided by the square root of n. We have T sub C, perfect. So now we can figure out what E is. E is equal to T sub C times S divided by the square root of n. And there we go. So this is our margin of error. And just like we did before, we have our lower bound and our upper bound. So what we're doing is we're getting our sample statistic, which in this case is X bar. And we're subtracting our margin of error here, adding our margin of error over here. And that's what we have to do there. So here we have our lower bound and we have our upper bound. So now for the lower bound, we're going lower in numbers. So we're going to subtract. So equals our mean minus our margin of error. And here we have our mean plus our margin of error. And there we go. So we would say that it's somewhere between 38,000 and, well, I'm going to estimate 32,000, 42,000. And now let's see if we missed anything. So data are obtained from a simple random sample. In addition, there are likely thousands of 2014 Toyota Camry vehicles on the road. So the sample mean or sample size is relatively small to the sample population. The figure shows the normal probability plot. Okay, cool. So that means that we are able to use all of this. So it's reasonable to conclude that the sample data come from a population that is normally distributed. The box plot does not reveal any outliers. Requirements for constructing the confidence interval are satisfied using option 1. If you're using option 2, blah, blah, blah. All right, so looking at our lower estimate, so our lower bound, we have X bar minus our margin of error, and that gave us 26.83. Ooh, that gave us something different. Okay, so I see where the mistake was. So for some reason, and of course doesn't want to go backwards. Okay. So for some reason, the data that was displayed on this slide is not the data that should have been displayed on that slide. So here we're looking at the fuel economy. So this is cars.com. But if we go back in time, we could see that the data for the fuel economy was already one of the examples that they gave us. There we go. So it ended up being this data set, fueleconomy.com.org, which is the data that we had right here. So instead of like freaking out, we could just do this and paste it over here. So here the data does kind of look a little bit different. So average, do we have, nope, we need this data. And sample standard deviation, same thing here for the whole data set here. standard deviation divided by n, and n in this case is not 12, it's 1, 2, 3, 4 by 1, 2, 3, 4. So here it's going to be 16. So just fixing that, degrees of freedom here, T sub C here, and now we have these values here. So this is actually not money. So what we could do is come over here to home and just say that it's general. So not money. And not money. All right, much better. So now our data matches what they have over here. So let's just go back. There we go. Okay, so X bar was 28.1, X bar 28.1, just like we had earlier. And from here, we have our critical value T sub C, our critical value 2.131, 2.131. And we have S divided by the square root of N. So this is going to be a little bit different from what we have. S divided by the square root of N, which is 16. And our lower bound ends up being this value here. So remember, we took a slightly different approach. We found out what E was. So that way we could just subtract it to that one and add it to this one. But either way, we ended up with the exact same values that they did. Only a tiny bit more accurate because we kind of did it a little bit different. All right, step 5 is our explanation. So we are 90% confident that the mean miles per gallon of a 2014 Toyota Camry car is between 26.83 and 29.37 miles per gallon. Here they use technology in a different way. So if you are copying, if you are kind of like working off of the slides instead of watching the videos, be sure to make note of that with the slideshow. All right, next, determine the sample size needed to estimate the population mean within a specific or specified margin of error. All right, so determining the sample size n. So the sample size required to estimate the population mean, mu, with the level of confidence 1 minus alpha times 100%, with a specified margin of error E is given by these values right here. So this time we don't need to have a p-hat. What we need is our critical value, our margin of error, and S, our standard deviation, or sample standard deviation. So we again consider the problem estimating the miles per gallon of a 2014 Toyota Camry. How large a sample size is required to estimate the mean miles per gallon with 0.5 miles per gallon with a 95% confidence level? All right, so again, we need n is equal to z sub alpha over 2 times s over e squared. So now with this data, so we again consider the problem estimating the miles per gallon of 2014 Toyota Camry. How large a sample size is required to estimate the mean miles per gallon within 0.05 miles, 0.05 or 0.5 miles per gallon with 95% confidence interval. So that tells us that E is 0.5 and with 95% confidence. All right, so with that, ooh, it looks like we lost our stuff. Okay, I guess we lost it forever. Okay, no big deal. So miles per gallon, we need 0.5. So E is equal to 0.5. And we have 95% confidence. And that should be everything that we need. Okay, so now the equation for n, we said n is equal to our z sub alpha over 2, or our critical value for z, times our standard deviation, and we're dividing by our estimate squared. All right, so be very, very careful because this time we have a z-score that we're looking for, a critical z-value. So z-value, we're using our normal distribution, and we could kind of go from there. All right, so with 95% confidence, that means that 95% of our data is going to land here in the middle. That means that 5% is going to be on either side, or 5% is going to be shared on either side. So that's going to be 0.025 here, 0.025 over here. So our critical z value is going to come from 90 or 0.975. So our critical z value is going to be from a normal distribution, because that's where z-scores come from. Normal distribution or normal inverse. Do we need an area or do we have an area? We have an area that we need an associated z-score for. So we have 0.975. Because we're looking at the standard normal distribution, it's going to be a mean of 0 with standard deviation of 1. And we have z-score. Next, we need s. Oh, we already have s. All right, the next thing we need is e. Okay, e was given to us, so we have e. In this case, for this problem, it's going to be equal to 0.5. Now from there, we can figure out what n is. So again, n is equal to, in parentheses, we have all of this stuff. So in parentheses, we have everything that we're going to square, but then we also need parentheses for the numerator. So the numerator is z sub c times our standard deviation, which was already given to us here, and close parentheses for the numerator, divided by e, our denominator. Now we're going to close the parentheses for everything there, and we raise this all to the power 2. And clear this out. So we have 8.07 or 8.87.03, and let's see what they got. They rounded up. Oh, they went a little bit different than we did. All right, either way, we still have that value. We're always going to bump it up one more. So we're going to bump it up to 88 instead of 87, because remember, we still need that 0.04 of a person in order to match this data here. So round up to 88. So the sample size of n equaling 88 results in an interval estimate of the population mean miles per gallon of a Toyota or 2014 Toyota Camry with margin of error 0.5 miles per gallon with a 95% level of confidence. And that's it for this section. If you guys have any questions, please email me as soon as possible. And if not, good luck on your homework. Bye.